things we had to do in lab this week was run the chi-square test of independence, which is kind of mathy and statistical, and some folks were having problems. So let's talk about it. Here is the symbol for the chi-square test of independence, and sort of right off the jump, people have issues with this because they see a square, and so when they're done doing calculations, people do all kinds of weird things like try to take a square root, and basically you can think of this as just a symbol. The square isn't going to go anywhere, it's not going to do anything. Like, you could plug in a y for all of this if you wanted to. But basically what I'm saying here is don't worry about the square, we're not going to do anything with it. So let's look at our actual formula. And this looks pretty bad, right? There's this big sigma notation here. I equals 1. There, what is n? Where does n even come from? We've got these O's and these E's and all of this stuff. And I just want to let you know that, first of all, you don't have to memorize this equation. You should know how to use it, and we're going to talk about how to do that, but you don't have to memorize it. And we're going to talk about what each of these symbols means and hopefully demystify this a little bit so it's at least a little less. Now, the other part that makes this kind of wonky is you have to do all these calculations, and then you have to like consult this table to figure out where your calculation is even meaningful. And we're going to talk about how to use this table, and again, hopefully we'll make this a little less scary. So let's say we have some situation where we have incomplete dominance, and these represent flowers. And so if a plant has a big R allele, its flowers are going to be red. If a plant has a little r allele, if it is homozygous recessive, it is going to have white flowers. If a plant has a big R and a little r, so it is heterozygous, it's going to have these pink flowers. And so we can figure out, if we cross a red flower and a white flower, what is it that the offspring of this cross should theoretically look like. And they should all be heterozygous. Every single one of these flowers from this cross should turn out pink because, again, we learned about this. This is incomplete dominance. The heterozygous individuals are different than the homozygous dominant and the homozygous recessive, but they should be 100% pink in this case. But what happens if we cross a pink flower and a pink flower, if we cross two heterozygous individuals? Well, we wind up with this 1 to 2 to 1, or 1/4 to 1/4 to 1/2 ratio, because we wind up with homozygous dominant red here, heterozygous pink here, and homozygous recessive white here. So again, 1 to 2 to 1. So how do we actually apply this? And again, let's say we're some sort of flower monger or whatever, and we want to get a certain number of pink flowers, white flowers, and red flowers. Well, if we follow this pattern, we can actually predict how many we should be getting. And then we can use chi-square to determine, is there some other factor here leading potentially to these differences? So let's make ourselves a table so we can think about how this is supposed to work. So here we'll have our ratio of flowers that we're expecting, which is again 1/4, 2/4, 1/4. And I said 1 to 2 to 1 earlier. That's what I'm talking about here, is 1 red for every 2 white for every 1 pink, 1 to 2 to 1, 1/4 to 2/4 to 1/4. And remember, that comes from our Punnett square. So if we had 1,000 flowers, how many would we expect for each phenotype? Well, this would be 1/4 of them, 1/4 times 1,000. This would be half of them, 1/2 times 1,000. This would be 1/4 of them, 1/4 times 1,000. This is kind of a contrived example. You probably wouldn't have 1,000, but that's okay. Thank you for bearing with me on that. Just makes the math a little bit easier. So then we have our observed flowers, and where do we get these data from? How do we actually observe this? Well, you just go and look and see what kind of flowers actually grew. Okay, so let's keep going now. We have our expected values that we got from our formula with our Punnett square. We have our observed values that we got from just going and looking at how many flowers we had. Come on, computer. Stick that up in the corner so we can do some math with it. So let's go back and look at, our chi-square formula here. And chi-square equals the sum of the observed minus expected squared divided by expected, which again is horrible looking formula, but it's really just a few simple math steps. So let's make a table here, and we can put our observed minus our expected values in this first column, and we're going to add to this as we work our way through. So here is our observed and our expected values. We observed 267, we expected 250, so we can just plug that in right there. The next one, for white flowers, we observed 457, but we expected 500. Just plug that one in right there. That gives us negative 43. And lastly, our pink values, we observed 267 and we expected 250. That gives us 26. So the next thing that we have to do is we just have to simply square these values. So 17 squared, negative 43 squared, 26 squared, and that gives us those values there. 289, 1849, 676. So moving on to the next part of this, now we have to take those and divide them by our expected values. So here is our observed minus expected squared. Where do we get our, we're going to put that in the denominator. Now where do we get our expected values from? Well, we expected 250, so we're going to divide that by 250. Next, what is our observed minus expected squared? It's 1849. We're going to put that in the numerator, and we're going to put our 500 in the denominator. And lastly, we have 676. What was our expected value? 250. We're going to put that in the denominator there. And if we crunch all those, those are the numbers that we wind up with. And so now for the worst part, the most horrible seeming part here, the sigma. How on earth do we run this sigma calculation? Well, we just add these three numbers. So I'll put the 6 and 8 and 4 is 18, put the 8 there, carry the 1. We'll put the 5 down there, carry the 1 again. And we wind up with 7.558. That's how you do a sigma. Sigma just means add all the stuff up. And so that's what we did. We just added these three numbers together. Okay, 7.558 is our chi-square value. So now we have this table. And this table is going to tell us basically the number at which these two observed and expected numbers become statistically significant or statistically different. So how do we interpret this? Well, the first thing that you see here is this first column, which is DF, which stands for degrees of freedom. And what on earth does that mean? Degrees of freedom just means the number of categories that you have minus 1, which I'm not going to go into why it's that. That's just something that you kind of need to memorize. How many categories did we have just now? We had red flowers, we had white flowers, and we had pink flowers, right? So we had 3 categories. What will our degrees of freedom be? 3 minus 1, which equals 2, and here's the number that we calculated. I just put it up here to remind us. So we go to this 2 row here, okay? Our degrees of freedom is 2, so our value we're looking for is somewhere here. Now, hands-on told you guys to look at a 95% confidence level, which, by the way, 95% confidence is not really all that great. That means that 1 out of 20 times our values will statistically deviate from our expectation on average, which is 1 out of 20. Which means if we were all in class together, if we were actually running this lab, that means that about one of you would just accidentally have numbers that statistically significantly deviated from what our expectation is. So 95% seemed really high, not actually all that great. So this is our 95% column here, and so we're going to look here, and we're looking at this number. And our question is the number that we calculated bigger than this, or is it smaller than this? And here's our number up here in the top left. Our number is bigger than this. And so there is a statistical difference between our observed and our expected values. That's what's kind of interesting now, is why are we seeing this statistical difference? Why are these numbers different from why is our observed value different from our expected value? And that's where the biology gets interesting. Uh, maybe it's that heterozygous individuals are dying before they can um, turn into flowers. I don't know what it is, but that's why this is interesting biologically. Is there some evolutionary force acting here? Is it that these plants aren't actually? Is it that this particular phenotype isn't actually a Mendelian trait? Okay, that's where this becomes interesting, and that's why this test is done, and why this test is done in biology. Um, Yep, I think that's about it. Again, if you guys have questions about this or any of the numbers that we just used or any part of this process, please shoot me an email. Please come by my office hours.